Have you ever paused to wonder how the different, distant parts of your body, separated by inches of bone and muscle, manage to work in such perfect, silent harmony? How does your heart know to beat faster when your muscles require more oxygen? Or how does your liver know exactly when to release stored energy during a long walk, even when you aren't consciously thinking about it? We often credit our brain and our nerves for this coordination, imagining a vast web of electrical wires pulsing with commands. But what if I told you there is another system, one that is completely wireless, invisible, and operates through the gentle flow of your own lifeblood? Tonight, we begin our journey by exploring this hidden network, the endocrine system. It is a world of chemical whispers and molecular keys, a system that manages the slow, deep rhythms of your life, your growth, your metabolism, and your very mood. In this opening lesson, we will lay the foundation for everything to follow. We are going to define the players in this grand biological drama, from the glands that act as broadcasting stations to the hormones that serve as the messages themselves. We will explore how these messages travel, and perhaps most importantly, how they find exactly the right destination among trillions of possibilities. Think of this as unrolling a grand ancient map. Before we can study the specific landmarks, we must first understand the language of the terrain. Lesson 1. Introduction to the endocrine system. To truly understand the endocrine system, you might first picture the human body as an incredibly vast and bustling city. For any city to thrive, it requires two distinct types of communication. The first is like a fiber optic network, the nervous system. It sends lightning-fast electrical signals to specific addresses to handle immediate needs, like a reflex or a sudden movement. But a city also needs a different kind of communication, something more like a radio broadcast or a series of carefully written letters sent through the air. This is the endocrine system. It doesn't use wires. Instead, it uses specialized chemical messengers called hormones. The word hormone is derived from an ancient Greek word hormone, which translates literally to that which sets in motion. I find that such a beautiful way to think of it. These tiny molecules are the primary catalysts for almost every major change your body undergoes. They are produced by specialized structures known as endocrine glands. Now it is important to distinguish these from other glands you might be familiar with, such as your sweat glands, or the glands that produce saliva. Those are called exocrine glands, and they use little tubes, or ducts, to carry their secretions to a specific surface. Endocrine glands, however, are entirely different. They are ductless. Because they have no tubes to guide them, they release their precious chemical cargo directly into the interstitial fluid surrounding them, where it quickly diffuses into the smallest of your blood vessels, the capillaries. Once a hormone enters the bloodstream, it is like a message in a bottle cast into a vast circling ocean. It is carried by the flow of your blood to every corner of your anatomy. From the crown of your head to the tips of your toes. You might wonder, if these hormones are floating everywhere in the blood, why doesn't every part of the body react to every single message? Why doesn't a growth hormone, for instance, cause your heart to beat faster? Or an adrenaline molecule cause your bones to grow? The answer lies in the incredible specificity of target cells. Imagine that every hormone is a very uniquely shaped molecular key, As it travels through the bloodstream, it brushes against millions of cells. Most of those cells ignore it entirely. They are like locked doors that the key simply doesn't fit. But eventually, that hormone encounters a cell that possesses a specific receptor. These receptors are complex protein structures located either on the cell's outer membrane or tucked away deep inside its nucleus. These receptors are the locks. Only when the hormone key finds its receptor lock does the message get delivered. This binding action is what triggers the cell to change its behavior, whether that means producing a new protein, opening a channel for nutrients, or altering its metabolic speed. Take a moment to let that idea find its place. Even as you lie here, resting and breathing softly, trillions of these chemical keys are drifting through your veins, seeking their specific locks, ensuring that your body remains in a state of perfect, quiet balance. To appreciate the endocrine system, we must look at it through the lens of history and compare it to its faster sibling, the nervous system. For a long time, scientists believed the nervous system was the sole ruler of the body. It wasn't until the early 20th century, around 1902, that two English physiologists, William Bayliss and Ernest Starling, discovered the first hormone, which they named secretin. They found that even when the nerves to the digestive system were severed, the body could still signal the pancreas to release digestive juices. They realized there had to be a chemical reflex, a message traveling through the blood rather than through a nerve fiber. This discovery opened our eyes to the reality that we are governed by more than just electricity. We are governed by chemistry. As we compare the endocrine and nervous systems, we see a study in contrasts. The nervous system is built for speed and precision. Its effects are almost instantaneous, but they are also very brief. Once the electrical pulse stops, the effect ends. The endocrine system, however, is built for duration. Because hormones must travel through the blood and then be processed by cells, their effects take longer to appear, sometimes minutes, sometimes hours, or even days. But once they arrive, their influence is deep and long-lasting. They don't just tell a muscle to twitch, they tell a body to grow, or a heart to change its long-term rhythm. The ultimate goal of all this chemical signaling is a concept that is central to all of biology: homeostasis. If you were to look at a university textbook, you would see this word on almost every page. It comes from the Greek words for same and steady. Homeostasis is your body's relentless, silent pursuit of stability in a world that is constantly changing. Your internal temperature, your blood sugar levels, your hydration, these are all kept within a very narrow, safe range by the endocrine system. Think of it like a master conductor overseeing an orchestra. If the violins begin to play too loudly, the conductor gestures for them to soften. If the percussion is too slow, he encourages them to pick up the pace. The endocrine system is that conductor. It doesn't play the instruments itself. It sends the signals that ensure every section of your biological orchestra is in tune with the others. If your mind is still following along, try visualizing this process. See the glands as quiet, glowing lanterns tucked away in the brain, the neck, and the abdomen. See the hormones as soft pulses of light entering the rivers of the blood, drifting patiently until they find their matching light at a target cell. It is a slow, methodical, and incredibly reliable system. You don't have to worry about memorizing every molecular pathway. Just let the logic of it wash over you. The body is designed to take care of itself. And the endocrine system is the primary tool it uses to maintain that beautiful internal peace. Real-world relevance and synthesis connecting the dots. You might be asking yourself, how does this apply to my life right now? The truth is, you are experiencing the work of your endocrine system at this very moment. As the room grows dim and you prepare for sleep, your brain is noticing the lack of light and signaling a tiny gland to release a hormone that tells your body it is time to rest. When you wake up tomorrow and feel a surge of hunger, that is another hormone produced in your stomach, telling your brain that your energy stores are low. This system is the reason you grew from a small child into the person you are today. It is the reason your body can react to a sudden fright with a burst of energy. And it is the reason you can maintain your energy throughout a long day of work. When we talk about hormonal balance, we aren't just using a buzzword. We are describing the very foundation of health. When the endocrine system is working correctly, you feel energized, your mood is stable, and your body functions efficiently. When it is out of balance, if a gland produces too much or too little of a hormone, it can affect everything from your sleep patterns to your bone density. So you see, this isn't just a collection of definitions in a textbook. It is the principle that explains why you feel the way you feel. It is the mechanism that allows your body to adapt to the changing seasons, the food you eat, and the stresses of your life. It is a testament to the incredible complexity and intelligence of your own biology. We are not just machines with wires. We are chemical masterpieces, constantly communicating with ourselves in a language of molecules and receptors. We have now successfully mapped out the general landscape. We have met the messengers, identified the glands, and understood the importance of the target cells and their receptors. We have seen how the endocrine system acts as the slow, steady, and profound coordinator of your life's many rhythms. But understanding that a message exists is only half the story. The next question we must answer is, how does the message actually get delivered once it reaches the cell's door? What happens at that molecular lock that causes such a massive change in the cell's behavior? Having now grasped the overall structure of the system, we are perfectly prepared to appreciate its function at the microscopic level. So, when we return in our next lesson, we will begin our study of the mechanisms of hormone action. We will look closer at those molecular keys and discover the different ways they unlock the secrets of the cell. For now, let these thoughts rest. You have done the hard work of laying the foundation. Let the idea of your body's silent chemical harmony carry you into a deeper state of relaxation. Our journey has only just begun. Lesson 2. Mechanisms of hormone action. Imagine, if you will, the microscopic world of a single cell. It is a bustling, self-contained universe, protected from the outside world by a thin, shimmering barrier known as the plasma membrane. This membrane is the cell's sanctuary, a discerning gatekeeper that decides what may enter and what must stay out. For a hormone drifting through the vast, dark rivers of your bloodstream, this membrane represents the final frontier. The question we must answer tonight is one of profound biological mystery. How does a tiny chemical messenger, floating in the fluid outside a cell, manage to reach through this barrier and fundamentally change the way that cell behaves? This process is not a simple one. and yet it happens millions of times every second within your body. It is a story of molecular handshakes, second messengers, and the rewriting of genetic instructions. In this lesson, we are going to look closely at the two primary ways hormones communicate with their targets. We will explore the doorbell mechanism used by water-soluble hormones, where the message is passed from the outside in, and the direct entry mechanism used by lipid-soluble hormones, where the messenger walks straight into the cell's inner sanctum. By understanding these mechanisms, we begin to see how the endocrine system can orchestrate both the sudden thrum of a racing heart and the slow, years-long transformation of a growing child. To understand how a hormone acts, we must first look at its chemical personality. In the world of biology, a hormone's personality is defined by whether it likes water or whether it prefers fats. This single characteristic, its solubility, determines the entire strategy it must use to deliver its message. The first family of hormones we encounter are the water-soluble hormones. These are usually constructed from amino acids, the building blocks of proteins. Because they are polar molecules, they dissolve easily in your blood, which is mostly water, but they find themselves completely blocked by the cell membrane. You see, the cell membrane is composed of a double layer of lipids or fats. In the laws of chemistry, like dissolves like, and since water and oil do not mix, these protein-based hormones cannot simply slip through the fatty barrier. For these water-soluble hormones, the cell membrane is like a sturdy front door that remains locked. Because the hormone cannot enter the house, it must rely on a relay system. This is what we call a second messenger system. The hormone itself is the first messenger. It arrives at the cell and binds to a specific receptor protein that is embedded in the membrane, with its hand reaching out into the extracellular fluid. When the hormone binds to this receptor, it is like ringing a doorbell. The visitor stays on the porch, but the sound of the bell echoes through the hallways of the cell, triggering a series of internal events. Inside the cell, this doorbell usually activates a middleman known as a G protein. This protein acts like a courier, scurrying along the inside of the membrane to activate an enzyme. This enzyme then produces the second messenger, most commonly a molecule called cyclic AMP, or simply CAMP. This CAMP is the messenger that actually carries the instructions to the cell's machinery, turning on enzymes or opening channels. It is a beautiful indirect way of communicating, allowing the hormone to exert its influence without ever having to step foot inside the cell's private space. The second family of hormones follows a completely different set of rules. These are the lipid-soluble hormones, which include the steroid hormones derived from cholesterol, as well as the hormones produced by your thyroid gland. Because these messengers are made of lipids, the fatty cell membrane is not a barrier to them. It is an open door. They can dissolve right into the membrane and slip through to the other side with ease. Once inside, these lipid-soluble hormones do not need a second messenger. They travel through the cytoplasm of the cell, often heading straight for the nucleus, the library of the cell where the DNA blueprints are kept. Within the cytoplasm or the nucleus, they find their specific receptors. Together, the hormone and the receptor form a complex that binds directly to the cell's DNA. This is a very intimate form of communication. By binding to the DNA, the hormone can turn specific genes on or off essentially ordering the cell to build entirely new proteins or structures. If the water-soluble hormone is a visitor ringing the doorbell, the lipid-soluble hormone is a contractor with a key to the house who walks in and begins rewriting the blueprints for the building itself. If we look even deeper into these processes, we discover one of the most remarkable features of the second messenger system: the power of amplification. You might wonder why the body would go through such a complex indirect process as the CAMP pathway when it could just send the messenger inside. The reason is efficiency. When one single hormone molecule binds to a receptor on the outside of a cell, it doesn't just produce one second messenger. That single doorbell ring can activate several G proteins. Each of those G proteins can activate an enzyme that produces hundreds of CAMP molecules. Each CAMP molecule, in turn, can activate many more enzymes. This creates a magnificent cascade effect. A tiny, almost infinitesimal amount of a hormone in the blood can result in a massive, lightning-fast response within the target cell. This is why a sudden surge of adrenaline can make your entire body react in a heartbeat. The signal is being amplified thousands of times over as it moves from the membrane into the cell's interior. It is a biological megaphone, ensuring that even the quietest chemical whisper is heard as a loud command. In contrast, the mechanism of direct gene activation used by steroid hormones is not about speed. It is about architectural change. Because these hormones must enter the nucleus, locate the correct gene, and then wait for the cell to actually manufacture new proteins through the processes of transcription and translation, the effects are not immediate. It can take hours or even days for the results of a steroid hormone's message to become visible. However, these changes are often much more permanent. While a water-soluble hormone might change the activity of an enzyme that is already there, a lipid-soluble hormone can change the very nature of what the cell is and what it does. History shows us how we came to understand these two distinct paths. It was Earl Sutherland, an American pharmacologist, who won the Nobel Prize in 1971 for his discovery of CAMP and the second messenger system. Before his work, we didn't understand how hormones like epinephrine could affect the liver so quickly. His discovery showed us that the cell has its own internal language, and the hormone is simply the spark that starts the conversation. On the other hand, our understanding of steroid action came from observing the long-term changes in development, how certain hormones could literally reshape the body over time. Together, these two mechanisms provide the endocrine system with a full range of temporal control, from the instantaneous to the epical. Take a moment to let the logic of this wash over you. If your mind is still following along, try visualizing the difference in pace. One system is like a light switch, flicking on an existing lamp to illuminate a room instantly. The other is like a gardener planting a seed. You won't see the flower tonight, but the seed is changing the very landscape of the garden for the season to come. So how do we see these two different mechanisms at play in our daily lives? The most vivid example is the difference between a rush and a growth. When you are startled by a loud noise or a sudden movement, your adrenal glands release epinephrine, a water-soluble hormone. Because it uses the second messenger system with its rapid amplification, your heart rate increases and your pupils dilate in a fraction of a second. This is the light switch in action. The body needs an immediate response to survive, and the second messenger system provides it. Compare this to the process of puberty or the growth of your bones and muscles. These processes are driven largely by steroid hormones and growth factors that use direct gene activation. You don't wake up one morning having grown 3 inches taller because of a sudden hormone surge. Instead, these lipid-soluble messengers are constantly entering your cells, interacting with your DNA, and slowly building the new proteins that allow your body to reshape itself. This is the gardener at work, patiently tending to the long-term architecture of your life. This distinction also explains much of modern medicine. When doctors treat a severe allergic reaction or an asthma attack, they often use medications that mimic water-soluble hormones because they need an effect that begins in seconds. However, when treating chronic conditions like inflammation or certain hormonal deficiencies, they may use steroid-based medications. These don't work instantly, which is why a patient might need to take them for several days before feeling the full benefit. The medication is literally reprogramming the cells, and that takes time. Understanding these mechanisms helps us appreciate the incredible precision of our biology. Your body knows which messages require a high-speed relay and which ones require a deep, genetic conversation. It is a system that understands both the urgency of the moment and the necessity of the future. As you lie here, your body is using both of these paths. Some cells are reacting instantly to maintain your blood pressure as you change positions, while others are slowly repairing and rebuilding your tissues as you drift toward sleep. We have now explored the 2 primary ways the chemical messengers of the endocrine system deliver their instructions. We have seen the rapid-fire relay of the second messenger and the deep, transformative power of direct gene activation. We understand how the hormone key interacts with the cell lock, whether that lock is on the front door or deep within the inner office. But who decides when these keys should be sent out? How does the body know that it is time for a rush of adrenaline or a season of growth? To find the answer, we must travel back up the body and return to the brain. We need to visit the master architects of this entire system, the ones who monitor the state of the body and issue the commands that keep the chemical messengers flowing. Let's hold that thought here, a complete piece of the puzzle. Our next lesson will hand us the adjacent piece, which is the study of the hypothalamus and pituitary gland. We will meet the command center that bridges the gap between your thoughts, your environment, and your very chemistry. But for now, let those molecular mechanisms rest in your mind. The cell is safe, the message has been delivered, and the body is in balance. Feel the quiet efficiency of your own biology as it continues its silent work, and allow yourself to drift even deeper into a calm, restorative sleep. Lesson 3. The hypothalamus and pituitary gland. If the endocrine system is an orchestra, and the hormones are the music that travels through the air, we must eventually ask, who is the conductor? Who sits at the podium, watching the tempo of our breathing, the temperature of our skin, and the rhythm of our heart, deciding exactly when the woodwinds should rise or the percussion should fall? To find this master architect, we must travel deep into the protected center of the brain, to a small but vital region that serves as the ultimate bridge between our thoughts and our chemistry. Tonight we explore the profound relationship between the hypothalamus and the pituitary gland. This partnership is perhaps the most critical coordination point in the entire human body. It is here that the lightning-fast impulses of the nervous system are translated into the slow, steady instructions of the endocrine system. We are visiting the command center of your biology, the place where your brain decides how your body should feel, grow, and survive. Deep within the brain, nestled just above the roof of your mouth and below the thalamus, lies a small, almond-sized structure called the hypothalamus. Despite its modest size, the hypothalamus is arguably the most important homeostatic organ in the body. It is a tireless sentinel. It constantly monitors your blood, tasting its saltiness, measuring its temperature, and sensing the levels of various hormones circulating within it. The hypothalamus is part of the brain, meaning it is made of neurons and speaks the language of electricity. However, it is also the supreme commander of the endocrine system. It is the crucial translator that takes a neural signal, such as "I am cold," and turns it into a chemical command: increase metabolism to generate heat. Hanging just below the hypothalamus, suspended by a thin, delicate stalk called the infundibulum, is the pituitary gland. It is no larger than a pea, yet it has earned the title of the master gland because its secretions control the activity of so many other endocrine glands throughout the body. However, as we have seen in our earlier lessons, every master has a commander. The pituitary gland does not act on its own. It is the executive officer that carries out the orders issued by the hypothalamus. To understand how this command center works, we must look at the pituitary gland as two distinct organs that happen to be fused together. These are the anterior pituitary and the posterior pituitary. They may look like two halves of the same pea, but they have completely different origins and methods of operation. The posterior pituitary, located toward the back, is actually a physical extension of the hypothalamus itself. It is made of nervous tissue. The hypothalamus produces two specific hormones and sends them down long neural fibers into the posterior pituitary, where they are stored until the brain decides it is time to release them into the blood. The anterior pituitary, located in the front, is different. It is made of true glandular tissue, more like the other glands we will study later. Because there is no direct nerve connection between the hypothalamus and the anterior pituitary, they communicate through a specialized private plumbing system called the hypophyseal portal system. The hypothalamus secretes releasing hormones into a tiny network of blood vessels that travel directly down the stalk and into the anterior pituitary. These chemicals tell the anterior pituitary exactly which hormones to manufacture and release into the general circulation. It is a brilliant system of delegation. The hypothalamus senses the need, sends a local chemical memo to the anterior pituitary, and the anterior pituitary then broadcasts the final command to the rest of the body. Take a moment to let that hierarchy find its place in your mind. The brain senses the world. The hypothalamus translates that sense into a chemical message, and the pituitary gland broadcasts that message to the far reaches of your anatomy. It is a chain of command that ensures your body remains perfectly synchronized with your environment and your needs. To truly appreciate the elegance of this system, we should look at the specific hormones these two lobes manage. Let us start with the posterior pituitary, the storage room of the brain. It releases two vital molecules, oxytocin, an antidiuretic hormone, often called ADH. Oxytocin is often nicknamed the cuddle hormone or the bonding hormone. It is released in massive amounts during childbirth to stimulate contractions, but it is also released during social touch and bonding, acting as a chemical glue for human relationships. A DH, on the other hand, is the master of your hydration. When the hypothalamus senses that your blood is becoming too salty or concentrated, a sign that you are dehydrated, it tells the posterior pituitary to release ADH. This hormone travels to your kidneys and tells them to hold on to water rather than letting it leave as urine. It is the reason you don't dehydrate overnight while you sleep. The anterior pituitary, the factory, produces a much wider array of hormones, most of which are tropic hormones, meaning their job is to travel to another gland and tell it what to do. For example, it produces thyroid-stimulating hormone, TSH, which goes to the neck to wake up the thyroid. It produces adrenocorticotropic hormone, ACTH, which travels to the kidneys to activate the adrenal glands during stress. It also produces growth hormone, GH, which doesn't target a single gland, but instead talks to almost every cell in the body, particularly in the bones and muscles, telling them it is time to divide and grow. Historically, our understanding of this master-servant relationship is relatively recent. For centuries, the pituitary was thought to be a source of pituita, or phlegm, that drained into the nose, hence its name. It wasn't until the early 20th century, through the work of pioneers like Harvey Cushing, that we began to realize this tiny pea was the engine of human growth and metabolism. Later, in the 1970s, Roger Guillemin and Andrew Schally won the Nobel Prize for discovering those releasing hormones from the hypothalamus, proving once and for all that the brain was the secret puppet master of the endocrine system. If your mind is still following along, try visualizing this. Imagine the hypothalamus as a high-tech control room with screens displaying the body's internal vitals. When a correction is needed, the operator types a command and sends it down a short hallway to the pituitary. The pituitary, like a massive radio tower, then broadcasts that signal across the entire country of your body. It is an incredibly efficient way to ensure that the governor of the body, the brain, is always in control of the machinery of the body. You can see the work of this command center in almost every aspect of your daily life. Consider the simple act of drinking a large glass of water. Within minutes, your hypothalamus senses the dilution of your blood and tells your posterior pituitary to stop releasing ADH. Consequently, your kidneys begin to release more water, and you find yourself needing to visit the restroom. This is the command center maintaining your fluid balance with mathematical precision. Think also about the profound changes of puberty. This entire life stage is initiated by the hypothalamus. At a certain point in development, it begins pulsing a specific releasing hormone that tells the anterior pituitary to wake up the gonads. This starts the cascade of testosterone or estrogen that reshapes the body. It isn't a random event. It is a timed program executed by the command center in your brain. Even your response to a stressful day at work is managed here. When you perceive a challenge, your hypothalamus triggers the release of ACTH from the pituitary, which in turn tells your adrenal glands to produce cortisol. This keeps you alert and energized to handle the task at hand. However, the command center is also designed for rest. As you lie here now, in the quiet and the dark, your hypothalamus is shifting its priorities. It is lowering your core temperature and adjusting your metabolism, signaling to the rest of your glands that the day's work is done and the time for repair has begun. This bridge between the mind and the body is why our emotions can have such a physical impact on us. Because the hypothalamus is part of the brain's emotional center, the limbic system, it is directly influenced by how we feel. This is why prolonged stress or deep grief can affect our appetite, our growth, and our immune system. The thoughts in our head are translated directly into the chemicals in our blood through this tiny, magnificent interface. We have now explored the headquarters. We have met the commander, the hypothalamus, and the executive officer, the pituitary gland. We understand the chain of command and the specialized blood and nerve connections that allow the brain to rule the body's chemistry. We have seen how the commands are issued and the broad categories of instructions they contain. But a command is only useful if there is someone in the field to carry it out. Now that we understand how the orders are sent from the brain, it is time to follow one of those signals down the neck. We are going to visit the first major field office of the endocrine system, the gland that receives the signal to set the pace for your entire metabolism. Let's hold that thought here. A complete piece of the puzzle. Our next lesson will take us to the butterfly-shaped regulator of your energy, or the thyroid and parathyroid glands. We will see how the master's orders are put into practice to keep your internal fires burning at just the right temperature. But for now, let the command center rest. The sentinel is on duty, the signals are clear, and your body is being guided toward a deep and restorative peace. Feel the safety of being so well regulated and drift into the quiet. Lesson 4. The thyroid and parathyroid glands. As we continue our gentle descent from the command centers of the brain, we arrive at the base of the neck, a place where the endocrine system manages the very tempo of your life. In our previous sessions, we observed how the hypothalamus and pituitary gland act as the architects and generals, issuing the broad commands that govern the body. Now, we arrive at one of the most vital field offices in this entire network. Imagine a small, delicate structure, shaped like a butterfly with its wings outspread, wrapped protectively around your windpipe. This is the thyroid gland. Along with its tiny rice-sized neighbors, the parathyroid glands, it acts as the body's primary regulator of metabolic speed and mineral balance. Tonight, we will explore how this butterfly determines how quickly you burn energy, how much heat you produce, and how your bones maintain their strength. We are moving from the high-level strategy of the brain to the essential day-to-day operations of the body's engine room. To understand the thyroid gland, you must first understand the concept of a metabolic idle. Just as a car engine has a setting that determines how fast it runs while sitting at a stoplight, your body has a basal metabolic rate, the minimum amount of energy required to keep your heart beating, your lungs breathing, and your cells functioning while you are at rest. The thyroid gland is the hand on that dial. Located just below the larynx or voice box, the thyroid is a highly vascular, brownish-red organ consisting of two lobes connected by a bridge of tissue called the isthmus. It is unique among endocrine glands because it is the only one that stores its hormones in large quantities outside of its cells, tucked away in little sacs called follicles. The primary hormones produced here are thyroxine, often called T4, and triiodothyronine, known as T3. These names might sound technical, but the numbers simply refer to the number of iodine atoms attached to the molecule. This is a crucial detail. The thyroid is the only part of your body that has a significant use for iodine. It actively seeks out this element from the food you eat, trapping it and using it as the essential fuel to build its hormones. Without iodine, the thyroid cannot manufacture the instructions the body needs to stay energized. When the pituitary gland releases thyroid-stimulating hormone, or TSH, it acts like a finger pressing the start button on the thyroid. The thyroid then releases T3 and T4 into the bloodstream. Once released, these hormones travel to nearly every single cell in your body. Their effect is universal. They enter the cells and tell them to increase their consumption of oxygen and their breakdown of nutrients. This process generates heat, a phenomenon known as the calorogenic effect, and ensures that your internal chemical engines are running at the correct speed. Tucked away on the posterior, or back, surface of the thyroid are 4 tiny, inconspicuous structures, the parathyroid glands. Usually there are 2 on each lobe of the thyroid, though their number and exact location can vary. Despite their name and proximity, they have a job that is entirely independent of the thyroid's metabolic duties. The parathyroid glands are the body's dedicated monitors of calcium. They don't care about your energy levels. They care about the concentration of calcium ions in your blood. Calcium is often thought of only as a component of bones, but in the world of physiology, it is a vital electrical signal. Your nerves cannot fire, and your muscles, including your heart, cannot contract without the precise amount of calcium in the fluid surrounding them. The parathyroid glands produce parathyroid hormone, or PTH. This hormone is the body's primary tool for raising blood calcium levels when they dip too low. It is a precise and powerful regulator that acts on 3 different fronts. It tells your bones to release a bit of their stored calcium into the blood. It tells your kidneys to stop losing calcium in the urine. And it tells your intestines to absorb more calcium from the food you've eaten. It is a tireless guardian, ensuring that the electricity of your body never flickers out. To truly appreciate the elegance of the thyroid, we must look at how it manages its inventory. Most endocrine glands produce hormones and release them immediately, but the thyroid is like a careful warehouse manager. Within its follicles, it stores a sticky, protein-rich substance called colloid. This colloid contains a large protein called thyroglobulin, which acts as a scaffold for building T3 and T4. By storing these precursors in the colloid, the thyroid can maintain a supply of hormones that lasts for several weeks. This is a biological safety net. It means that even if you go without iodine for a few days, your metabolic rate remains stable. The relationship between T3 and T4 is also a masterpiece of efficiency. The thyroid produces much more T4, about 90% of its output, but T3 is much more potent and active. You can think of T4 as the reserve currency and T3 as the spending currency. When T4 reaches the target tissues, like the liver or the muscles, an enzyme strips away one iodine atom, converting it into the highly active T3. This allows the body to maintain a steady, circulating pool of hormone, that can be activated exactly where and when it is needed most. The history of our understanding of the thyroid is tied closely to the history of iodine. In centuries past, people living in mountainous regions far from the sea often developed large swellings in their necks called goiters. We now know that a goiter is the thyroid gland's desperate attempt to compensate for a lack of iodine. When the gland cannot find the iodine it needs to make T3 and T4, the pituitary gland senses the low hormone levels and screams at the thyroid with more and more TSH. The thyroid grows larger and larger, trying to catch any trace of iodine that might be in the blood. This discovery led to one of the most successful public health initiatives in history, the iodization of table salt, which virtually eliminated goiters in many parts of the world. Similarly, the discovery of the parathyroid glands was a slow realization. For a long time, surgeons removing a diseased thyroid would accidentally remove these tiny grains of rice as well. They were puzzled when the patients would soon develop severe muscle spasms and tremors. It wasn't until the late 19th and early 20th centuries that researchers realized these tiny dots were essential for life, controlling the very minerals that allow our muscles and nerves to function. Take a moment to let the logic of this wash over you. If your mind is still following along, try visualizing the thyroid as a warm, glowing butterfly, radiating heat and energy through your body, while the 4 parathyroids act as tiny, vigilant sentinels on its back, keeping watch over the mineral balance of your blood. It is a dual-purpose station, managing both the fire of metabolism and the stone of our skeleton. You see the influence of these glands every day. Often in the subtle ways your body responds to the environment. For instance, have you ever noticed that you seem to have a thicker skin against the cold in the winter than you do during a sudden cold snap in the summer? This is partly due to the thyroid. Over weeks of cold exposure, your hypothalamus and pituitary tell your thyroid to slightly increase its baseline production of T3 and T4. This raises your internal heat production, a process of long-term acclimatization. The thyroid is the reason we can adapt to different climates and seasons. We also see the thyroid's importance in how we feel. When the thyroid is hyperactive, producing too much hormone, the body's engine is racing. A person might feel constantly hot, anxious, and find their heart pounding even while resting. Whilst conversely, when the thyroid is sluggish or hypoactive, the engine idles too low. This leads to feelings of constant cold, fatigue, and a mental fog. It is a vivid reminder that our energy, our mood, and our very clarity of thought are deeply rooted in this small gland in our neck. The parathyroid glands, meanwhile, are working behind the scenes to protect your long-term skeletal health. Every time you skip a meal rich in calcium, your parathyroids gently borrow a bit of calcium from your bones to keep your blood level steady. This is why long-term nutrition is so vital. If the parathyroids are forced to borrow from the bone bank too often without a deposit of dietary calcium and vitamin D, the bones can become thin and brittle over time. Vitamin D is the essential partner here, as it acts like a key that allows the PTH to successfully pull calcium from the intestines. Without the sunshine vitamin, the parathyroids have to work much harder to maintain the balance. As you lie here now, in the quiet of the night, your thyroid is likely dialing back your metabolic rate. As your body temperature slightly drops and your breathing slows, the butterfly in your neck is settling into its nighttime rhythm. It is maintaining just enough warmth to keep your organs safe while allowing your systems to recover. At the same time, the parathyroids are performing their silent, minute-by-minute checks, ensuring that as your muscles relax into sleep, the electrical environment around your nerves remains perfectly stable. We have now explored the engine room of the neck. We have seen how the thyroid sets the pace for your energy and heat, and how the parathyroids guard the mineral integrity of your blood and bones. We understand the vital role of iodine and the delicate balance of the bone bank. We have seen how the master's orders from the brain are translated into the steady life-sustaining rhythms of metabolism. But what happens when the body faces a sudden, unexpected challenge? What if, instead of the steady idle of sleep or a calm day, the body is suddenly required to fight for its life or endure a period of intense, prolonged pressure? To find the answer, we must travel further down the body, past the heart and lungs, to the glands that sit like vigilant caps atop your kidneys. Let's hold that thought here, a complete piece of the puzzle. Our next lesson will introduce us to the body's survival specialists, the adrenal glands. We will explore the fight-or-flight response and the hormones that help us endure the long-term stresses of life. But for now, let the butterfly in your neck rest. The engine is idling perfectly, the minerals are balanced, and your body is in safe hands. Feel the warmth and the stability within you, and allow yourself to drift further into the quiet. Lesson 5. The adrenal glands. As we continue our slow, methodical journey down through the torso, we move past the heart and the lungs to a pair of organs that function as the body's ultimate survival specialists. If the thyroid is the steady idle of your engine, the glands we are about to discuss are the turbochargers and the emergency reserves. Perched like small, weathered tricorn hats atop each of your kidneys, the adrenal glands are the primary mediators of your response to the world's challenges. Whether you are facing a sudden sharp fright in a dark hallway, or the long, grueling pressure of a demanding month at work, these glands are the ones that translate those external pressures into internal action. Tonight, we will explore the dual nature of these remarkable structures, how they house two entirely different tissues in one small space, and how they manage the delicate balance between immediate survival and long-term endurance. We are visiting the crisis managers of your biological city. To understand the adrenal glands, you must first picture them as a complex, two-layered fortress. Although each gland is only about the size of a large grape, it is actually two distinct endocrine organs wrapped together. The inner core is known as the adrenal medulla, and the outer shell is called the adrenal cortex. They have different biological origins, different methods of communication, and they produce entirely different classes of hormones. The inner core, the adrenal medulla, is essentially a specialized extension of your nervous system. It is composed of modified neurons called chromaffin cells. When your brain perceives a sudden acute threat, the classic fight-or-flight scenario, it doesn't wait for a hormonal signal to travel through the blood. Instead, it sends a lightning-fast electrical impulse directly down a nerve to the medulla. In response, the medulla floods your bloodstream with catecholamines, epinephrine, which many of us know as adrenaline, and norepinephrine. These are water-soluble hormones that use the rapid-fire second messenger system we discussed in our earlier lessons. Within seconds, they reach your heart, causing it to pound, your lungs opening the airways, and your liver, demanding an immediate release of sugar for quick energy. This is your body's short-term stress response, a burst of power designed to save your life in an instant. Wrapped around this energetic core is the adrenal cortex, which accounts for about 80 to 90% of the gland's total mass. Unlike the medulla, the cortex is true glandular tissue, and it responds to the master gland signals from the pituitary in the brain. The cortex is further divided into 3 distinct zones, each producing a different type of steroid hormone derived from cholesterol. Because these are lipid-soluble, they work through the slower, more permanent direct gene activation method. The first zone, the outermost layer, produces mineralocorticoids, primarily aldosterone. Its job is to manage the minerals in your blood, specifically sodium and potassium. By telling the kidneys to hold on to salt, aldosterone ensures that you retain enough water to keep your blood pressure stable. The middle and largest zone produces glucocorticoids, the most famous of which is cortisol. This is the hormone of long-term stress and metabolic regulation. It ensures that even during periods of fasting or prolonged exertion, your brain always has enough glucose to function. The innermost zone of the cortex produces small amounts of gonadocorticoids, or adrenal sex hormones, which supplement the hormones produced by the ovaries and testes. Take a moment to let the logic of this architecture find its place. 1 gland, 2 layers, the inner core for the sudden flash of danger, and the outer shell for the long burn of daily survival and mineral balance. It is a masterpiece of biological engineering, ensuring that you are prepared for the tiger in the brush as well as the long winter ahead. If we look closer at the function of cortisol, the primary glucocorticoid, we see a hormone of incredible complexity. Cortisol is often unfairly labeled as merely a stress hormone, but in reality, it is essential for life even when we are perfectly calm. Its primary role is to maintain blood glucose levels between meals. It does this through a fascinating process called gluconeogenesis, literally the creation of new sugar. When your blood sugar begins to dip, cortisol tells your liver to take non-carbohydrate sources like fats and proteins and convert them into glucose. It is your body's way of ensuring the brain never runs out of fuel. However, during times of prolonged stress, cortisol levels remain elevated for long periods. This is managed by the HPA axis, the hypothalamic pituitary adrenal axis. The hypothalamus senses the stress and releases CRH. The pituitary receives this and releases ACTH, and the adrenal cortex responds by pumping out cortisol. This elevated cortisol keeps you alert and ensures your muscles have plenty of fuel, but it also intentionally suppresses non-essential systems to save energy. It dials down the immune system and reduces inflammation. This is why, historically, we have used synthetic versions of cortisol, like prednisone or hydrocortisone, to treat inflammatory conditions like rashes or joint pain. We are essentially borrowing the adrenal gland's natural ability to quiet the body's defenses. The story of the adrenal glands is also a story of medical discovery. In the mid-19th century, A British physician named Thomas Addison noticed a group of patients who suffered from extreme fatigue, weight loss, and a strange darkening of the skin. He discovered that their adrenal glands had been destroyed, usually by tuberculosis. This condition, now known as Addison's disease, was the first time we realize that these small caps on the kidneys were absolutely necessary for life. Without the mineralocorticoids to balance our salt and the glucocorticoids to manage our energy, the body simply cannot sustain its internal environment. Contrast this with the discovery of adrenaline. In the late 1890s, researchers found that injecting an extract from the adrenal medulla caused a massive rise in blood pressure. It was the first time a specific chemical was shown to have such a profound and immediate effect on the entire body. It revolutionized our understanding of how the brain could use chemistry to command the heart and lungs. And if your mind is still following along, try visualizing this. Imagine the adrenal glands as a high-security power plant. The inner core, the medulla, is the emergency generator that kicks in the millisecond the main grid fails. The outer cortex is the slow-moving management team that monitors the fuel reserves and the water pressure, making sure the city can survive a long-term shortage. Both are vital, and both are working in harmony right now as you rest. You experience the work of your adrenal glands in almost every high-stakes moment of your life. Have you ever felt that jolt when you almost trip on a stair? Or that sudden clarity and pounding heart when you have to speak in front of a crowd? That is your adrenal medulla performing its duty, flooding your system with epinephrine to prepare you for action. It is a primal, ancient response that has kept our ancestors alive for millennia. But you also feel the influence of the adrenal cortex in the quiet, persistent pressures of the modern world. When you are working late to finish a project, or dealing with a difficult personal situation, your HPA axis is active. Your cortisol levels rise to keep your brain fueled and your body going. This is why, after a long period of stress, people often find themselves getting sick. The same cortisol that gave them the energy to push through also suppressed their immune system. Your adrenal glands are constantly trying to balance the now with the later, making difficult choices about where to spend your body's limited energy. Even the simple act of standing up quickly requires your adrenals. As you move from lying down to standing, gravity wants to pull your blood toward your feet. Your adrenal glands immediately release a small amount of norepinephrine to constrict your blood vessels and aldosterone to manage your fluid volume, ensuring that enough blood reaches your brain so you don't feel faint. They are your body's constant gravity defiers and pressure regulators. As you lie here now, in the safety of your bed, your adrenal glands are finally shifting into a lower gear. Your epinephrine levels have dropped, allowing your heart rate to slow and your muscles to soften. Your cortisol levels are reaching their lowest point of the 24-hour cycle, a dip that traditionally happens around midnight. This drop in cortisol is a signal to your immune system to wake up and begin its nightly patrol, repairing tissues and fighting off any pathogens it encountered during the day. Your adrenals are stepping back, handing the reins over to the restorative processes of sleep. We have now explored the survival specialists of the mid-body. We have seen how the adrenal medulla handles the fight or flight sprint, and how the adrenal cortex manages the marathon of long-term stress and mineral balance. We understand the vital role of cortisol in fueling our brains and the essential nature of aldosterone in maintaining our pressure. We have seen how these small glands sit at the intersection of our nervous system and our endocrine system, guarding us against the world's dangers. But all this activity, the sprinting, the thinking, the enduring, requires a constant and reliable supply of energy. The cortisol we discussed can create sugar, but it is not the primary manager of the sugar we eat every day. To find the organ that acts as the master regulator of your body's fuel, we must look just a few inches away from the kidneys to a soft, feathery organ tucked behind the stomach. Let's hold that thought here, a complete piece of the puzzle. Our next lesson will introduce us to the guardian of your blood sugar, the pancreas, and glucose regulation. We will explore the delicate dance between insulin and glucagon, and how your body ensures every cell stays fed. But for now, let the adrenals rest. The crisis is over, the pressure is off, and your body is safe. Feel the deep, quiet stillness in your mid-back, and allow yourself to drift further into the quiet of the night. Lesson 6. The pancreas and glucose regulation. Imagine for a moment that every single cell in your body is a tiny flickering candle. For these trillions of candles to stay lit, they require a constant, steady supply of fuel, a simple sugar known as glucose. If the fuel line is too high, the flames grow dangerously large, damaging the very structures they are meant to power. If the fuel line is too low, the light flickers and dies, leaving the system in the dark. How does your body, across 24 hours of feasting and fasting, manage to keep that fuel line at a perfect, unwavering level? To find the answer, we must look behind the stomach to a soft, feathery organ that acts as the body's premier fuel manager. Tonight, we explore the dual nature of the pancreas and the intricate chemical dance of glucose regulation. We are moving from the survival hormones of the adrenals to the metabolic maintenance that sustains your life minute by minute throughout the day and deep into the night. The pancreas is a fascinating organ because it lives a double life. Most of its mass, about 99%, is dedicated to the digestive system, producing powerful enzymes that break down the food you eat. However, scattered throughout this digestive tissue like tiny, hidden islands in a vast sea are clusters of specialized endocrine cells. These clusters are known as the islets of Langerhans. Although they make up only a tiny fraction of the organ's weight, they are the sole guardians of your blood sugar levels. Within these islets, two primary types of cells act as the body's internal glucose sensors: the alpha cells and the beta cells. The beta cells are the producers of insulin, perhaps the most famous hormone in all of medicine. You might think of insulin as the hormone of plenty. When you sit down to a meal and your body begins to break down carbohydrates into glucose, your blood sugar levels rise. The beta cells sense this increase and immediately flood the bloodstream with insulin. As we discussed in our earlier lessons on mechanisms, insulin acts as a specific molecular key. It travels to your muscle and fat cells, binds to their receptors, and unlocks the doors, specialized transport proteins, that allow glucose to leave the blood and enter the cells. By doing this, insulin provides your cells with immediate energy, while simultaneously lowering your blood sugar back to a safe baseline level. But what happens when you haven't eaten for several hours or when you are deep in the middle of a long night's sleep. This is where the alpha cells and their hormone, glucagon, take center stage. Glucagon is the hormone of fasting. When your blood sugar levels begin to dip too low, the alpha cells sense the shortage and release glucagon into the blood. Glucagon travels primarily to the liver, which acts as the body's central warehouse for energy. It tells the liver to take its stored sugar, a complex molecule called glycogen, and break it back down into simple glucose to be released into the bloodstream. It is a perfect opposing force to insulin. While insulin moves sugar out of the blood and into storage, glucagon pulls sugar out of storage and back into the blood. Take a moment to let the logic of this balance find its place. Your body is never truly off when it comes to fuel management. Even as you rest, these two hormones are engaged in a constant, silent seesaw, ensuring that your brain, which is a greedy consumer of glucose and cannot store its own fuel, always has exactly what it needs to keep your heart beating and your lungs moving. To truly appreciate the elegance of this system, we must look at the concept of the negative feedback loop as it applies to the pancreas. In the world of engineering, a thermostat is the classic example of a negative feedback loop. When the room gets too hot, the sensor triggers the air conditioner to bring the temperature down. When it gets too cold, it triggers the heater. Your pancreas is a biological thermostat for energy. The set point is your ideal blood glucose level. Insulin is the cooling system that prevents overheating, and glucagon is the heating system that prevents a freeze. The storage of glucose is also a masterpiece of biological efficiency. We cannot simply have raw sugar floating around in high concentrations. It is chemically sticky and can damage blood vessels over time. Therefore, when insulin tells the liver and muscles to take in sugar, the body converts that glucose into glycogen. You can think of glucose as cash in your pocket, ready to spend immediately, and glycogen as money in the bank, a more stable, bundled form of wealth. If the bank of glycogen becomes full and there is still excess sugar in the blood, insulin assists in converting that extra energy into triglycerides, or body fat. This is the body's long-term savings account, a reserve designed to keep our ancestors alive through weeks of famine. The history of our understanding of the pancreas is one of the great triumphs of modern science. For centuries, we knew that some people suffered from a wasting disease, where their bodies couldn't seem to use the fuel they ate. It wasn't until 1889 that researchers realized removing the pancreas in dogs caused this exact condition. In the early 1920s, Frederick Banting and Charles Best, working in a small lab in Toronto, managed to isolate insulin for the first time. Before their discovery, a diagnosis of type 1 diabetes, where the beta cells are destroyed and cannot produce insulin, was a death sentence. Their work transformed a fatal condition into a manageable one, proving that by understanding the chemical whispers of the pancreas, we could literally save lives. If your mind is still following along, try visualizing this. Imagine the blood as a river carrying golden sparks of energy. When the river becomes too crowded with sparks, the islands of the pancreas release a fleet of small boats, insulin, to carry those sparks to the shore. When the river grows dark and empty, the islands release a different signal, glucagon, that tells the great warehouse on the hill to release its own stored sparks back into the water. It is a continuous, beautiful cycle of supply and demand. You feel the influence of your pancreas every single day, often in the way your energy levels wax and wane. Have you ever experienced a sugar crash after eating a very sweet dessert? This happens because the sudden spike in blood sugar causes your beta cells to release a massive overcorrection of insulin. The insulin works so efficiently that it pulls too much sugar out of the blood, leaving you feeling tired and shaky until your alpha cells can release enough glucagon to bring you back to balance. This is why complex carbohydrates, like whole grains, are often recommended. They release sugar slowly, allowing the pancreas to maintain a gentle, steady rhythm rather than a series of violent spikes. The pancreas also works in close coordination with the adrenal glands we discussed in our last lesson. Remember cortisol, the stress hormone that creates new sugar? When you are under stress, cortisol raises your blood sugar to prepare you for a challenge. Your pancreas must then work alongside that stress response, ensuring that while the sugar is available for your muscles, it doesn't stay in the blood long enough to cause damage. It is a multi-layered system where the fuel manager of the pancreas and the crisis manager of the adrenals are constantly talking to each other. As you lie here now, hours after your last meal, your pancreas is in its fasting mode. Your insulin levels are very low, allowing your cells to burn the energy they already have stored. Your alpha cells are likely releasing tiny, periodic pulses of glucagon to tap into your liver's glycogen reserves, keeping your blood sugar steady as your brain performs its nightly maintenance. This is the quietest time for your pancreas, a period of steady, low-level regulation that ensures your body remains fueled without any effort on your part. This system is a testament to your body's incredible foresight. It knows that you won't be eating for the next several hours, and it has already prepared the bank withdrawals necessary to keep you alive and healthy until breakfast. You are a self-sustaining engine, capable of managing your own energy with a precision that outshines any machine man has ever built. We have now explored the master of the body's fuel. We have seen how the islands of the pancreas monitor the blood, how insulin unlocks the doors to our cells, and how glucagon guards our reserves during the long hours of the night. We understand the balance of the fed and fasted states, and the vital importance of the liver as our chemical warehouse. We have seen how the body maintains the steady light of its trillions of cellular candles. But the endocrine system is not just about maintaining the individual. It is also about the future. Once the body is fueled, grown, and stable, it turns its attention to the continuation of life itself. To find the hormones that govern this profound transition, we must move to the glands that define our biological development and reproductive potential. Let's hold that thought here, a complete piece of the puzzle. Our next lesson will introduce us to the architects of gender and development, the gonads and reproductive hormones. We will explore the monthly rhythms and the lifelong cycles that allow life to begin anew. But for now, let the pancreas rest. The fuel is steady, the warehouse is secure, and your body is perfectly balanced. Feel the soft rhythmic pulse of your metabolism and allow yourself to drift further into the quiet of the night. Lesson 7. The gonads and reproductive hormones. As our quiet journey through the landscape of the human body continues, we move from the systems that sustain the individual, those that manage our energy, our minerals and our stress, to the system that looks toward the horizon. In our previous sessions, we explored the survival and maintenance offices of the endocrine system. Tonight, we turn our attention to the architects of the future. We are going to explore the gonads, the ovaries in the female and the testes in the male. These organs carry a dual responsibility that is unique in biology. They are both the producers of the seeds of life and the manufacturing centers for the powerful hormones that shape our physical identity. Have you ever considered how a single chemical signal can change the texture of a voice, the strength of a bone, or the very rhythm of a person's emotions? In this lesson, we will uncover the complex monthly cycles, the steady lifelong pulses, and the profound developmental changes driven by estrogen, progesterone, and testosterone. We are exploring the biological foundation of the continuation of the species. To understand the gonads, we must first return to the master gland in the brain. As we learned in our third lesson, the pituitary gland acts as the executive officer. It releases two specific hormones called gonadotropins, luteinizing hormone, or LH, and follicle stimulating hormone, or FSH. These two chemicals are the messengers that wake up the gonads and tell them it is time to work. Although men and women have different reproductive organs, and they both rely on these same two signals from the brain to begin the process of maturity and reproduction. In the female body, the primary gonads are the ovaries, two almond-sized organs nestled deep in the pelvic cavity. The ovaries are the source of two main classes of steroid hormones, estrogens and progesterone. Estrogens are the primary architects of the female form. During puberty, a surge in estrogen causes the development of secondary sexual characteristics, such as the widening of the hips and the growth of breast tissue. But estrogen's work is never done. Throughout a woman's life, it helps maintain bone density and regulates the cholesterol levels in the blood. Progesterone, on the other hand, is the hormone of preparation. Its primary job is to wait for a potential life to begin. Each month, it prepares the lining of the uterus to receive a fertilized egg, thickening the tissue and increasing its blood supply to create a nurturing environment. In the male body, the gonads are the testes, located within the scrotum. The specialized cells within the testes, called Leydig cells, are the manufacturing plants for testosterone, the primary male sex hormone. Just as estrogen shapes the female, testosterone is the architect of the male form. It drives the deepening of the voice, the growth of facial and body hair, and the significant increase in muscle mass and bone strength that occurs during puberty. Beyond these visible changes, testosterone is essential for the production of sperm and plays a continuous role in maintaining libido and overall energy levels. What makes these hormones fascinating from a mechanical perspective is that they are all steroid hormones, which we discussed in Lesson 2. They are synthesized from cholesterol, making them lipid-soluble. This means they don't ring a doorbell on the outside of a cell. They slip right through the fatty membrane, enter the nucleus, and speak directly to the DNA. When testosterone or estrogen enters a cell, it is literally changing which proteins that cell builds. They are the slow-acting but deep-reaching contractors of your biological identity, reshaping the building from the inside out over months and years. Take a moment to let the logic of this developmental system find its place. Your body isn't just a static machine. It is a work in progress, and constantly being refined and reshaped by these chemical signals that look toward the next generation. Deeper dive and context, adding the layers. To truly appreciate the elegance of reproductive endocrinology, we must look at the difference between steady state and cyclical regulation. In the male, the feedback loop is relatively stable. The hypothalamus and pituitary monitor testosterone levels in the blood. If they drop, more LH is released to stimulate the testes. If they rise too high, the system dials back. This creates a relatively constant day-to-day level of hormone that sustains male physiology throughout adulthood. In the female, however, the system is a masterpiece of complex timing known as the menstrual cycle. This is not a steady line, but a repeating wave that lasts approximately 28 days. And in the first half of the cycle, FSH stimulates the growth of a follicle in the ovary, which begins to pump out estrogen. As estrogen levels peak, they actually trigger a massive sudden surge of LH from the pituitary, one of the few examples of a positive feedback loop in the body. This surge causes ovulation, the release of an egg. After ovulation, the remains of the follicle transform into a temporary gland called the corpus luteum, which begins producing massive amounts of progesterone. If no pregnancy occurs, the corpus luteum withers, progesterone and estrogen levels crash, and the cycle begins anew. This monthly ebb and flow affects almost every system in the female body, from the temperature of the skin to the way the brain processes emotions. It is a biological rhythm that mirrors the phases of the moon, a constant internal season of preparation and renewal. The history of our understanding of these hormones is a story of profound social change. For millennia, the mysteries of reproduction were attributed to vital spirits or unknown forces. It wasn't until the 1920s and 30s that researchers like Edgar Allan and Edward Doisy managed to isolate estrogen and progesterone from the fluids of animals. This discovery eventually led to the development of hormonal birth control and hormone replacement therapies, giving humans, for the first time in history, a measure of control over their own reproductive chemistry. It was a realization that the most intimate parts of our identity were, at their core, managed by specific, identifiable molecules. If your mind is still following along, try visualizing this difference in pace, and imagine the male hormonal system as a steady, low hum, a pilot light that stays lit at the same height for decades. Now imagine the female system as a grand, slow-moving pendulum, swinging from the high energy of estrogen to the quiet, protective warmth of progesterone and back again. Both are essential for the survival of the human story. You can see the influence of these gonadal hormones in nearly every stage of the human experience. We see it most dramatically in the growth spurts of adolescence, where the sudden activation of these glands changes a child into an adult. But we also see it in the long-term health of our bodies as we age. For instance, after menopause, when a woman's estrogen levels naturally decline, her bones can become more porous and brittle, a condition known as osteoporosis. This is because estrogen was the silent protector that told the bone-building cells to keep working. In men, a gradual decline in testosterone over many decades can lead to a loss of muscle mass and changes in mood, a reminder that these hormones are as much about vitality as they are about reproduction. These hormones also interact deeply with the other systems we've studied. Do you remember the stress hormone cortisol from Lesson 5? Prolonged stress and high cortisol can actually shut down the reproductive signals from the hypothalamus. The body, in its wisdom, decides that if it is in a state of crisis, it is not a safe time to spend energy on reproduction. This is why high-stress lifestyles can often affect fertility or menstrual regularity. The crisis manager of the adrenals can temporarily overrule the future architect of the gonads. As you lie here now, these hormones are performing their quiet, nightly duties. In men, testosterone production often peaks during the deep stages of REM sleep, which is why a good night's rest is so vital for hormonal health. In women, depending on the day of their cycle, progesterone might be slightly raising the body's core temperature or promoting a sense of calm and sleepiness. Your body is using this time of rest to perform the chemical maintenance required to keep your reproductive and developmental systems in balance. This is a testament to the fact that your body is always looking forward. Even while you sleep, your endocrine system is preparing you for tomorrow, ensuring your bones stay strong, your tissues stay repaired, and your biological potential remains intact. You are part of a long, unbroken chain of life, sustained by these ancient chemical signals. We have now explored the architects of the future. We have seen how the ovaries and testes respond to the commands of the brain to shape our bodies and prepare us for the continuation of life. We understand the steady pulse of testosterone and the rhythmic wave of the menstrual cycle. We have seen how these lipid-soluble messengers reach deep into our DNA to define our physical journey from youth to old age. But as we talk about rhythms and cycles, we must ask, what keeps the clock? How does the body know when it is day and when it is night? How does the brain time the release of these hormones so that they align with the world outside? To find the answer, we must travel back up to the brain and to a tiny light-sensitive gland that acts as the body's internal chronometer. Let's hold that thought here, a complete piece of the puzzle. Our next lesson will introduce us to the guardian of your sleep and your sense of time, the pineal gland and circadian rhythms. We will explore the hormone of darkness and how your body syncs its internal chemistry with the rotation of the earth itself. But for now, let the gonads rest. The future is secure, the cycles are in motion, and your body is in perfect harmony. Feel the deep ancestral connection within you and allow yourself to drift further into the quiet of the night. Lesson 8. The pineal gland and circadian rhythms. As we climb back up from the depths of the body to the silent, protected spaces of the brain, we encounter a structure that is perhaps the most poetic of all the endocrine glands. For centuries, philosophers and early anatomists were baffled by a tiny pine cone-shaped organ nestled deep in the center of the skull, right at the crossroads of the brain's two hemispheres. The great philosopher René Descartes once famously speculated that this was the seat of the soul, the place where our spiritual and physical selves met. While modern science has given us a more biological explanation, the truth is no less wondrous. This is the pineal gland, and its primary task is to translate the movements of the heavens, the rising and setting of the sun, into the internal chemistry of your body. Tonight, we will explore the hormone of darkness, melatonin, and how this tiny gland acts as your body's master chronometer. We are moving into the study of time itself, how your body knows when to wake, when to eat, and most importantly for us right now, how it knows when it is time to drift into the restorative embrace of sleep. To understand the pineal gland, we must first understand the concept of a biological clock. Every living thing on this planet, from the simplest bacteria to the most complex human, has evolved to sync its internal processes with the 24-hour rotation of the Earth. This internal timing system is known as the circadian rhythm, a term derived from the Latin circa, meaning around, and diem, meaning day. The pineal gland is the primary broadcaster for this rhythm. Located in the hypothalamus, near the center of the brain, the pineal gland is a small reddish-gray structure that, despite its deep location, is intimately connected to the outside world through your eyes. The primary product of the pineal gland is the hormone melatonin. Unlike the other hormones we have studied, which respond to internal signals like blood sugar or calcium levels, melatonin responds almost exclusively to light and darkness. You might think of melatonin not as a sleep drug that forces the brain to shut down, but rather as a biological signal of darkness. It is the chemical equivalent of the sun going down and the streetlights coming on in a city. When your eyes, specifically specialized cells, in the retina called photosensitive ganglion cells, detect that the blue wavelength light of the sun is fading, they send a signal through a dedicated neural pathway to a tiny cluster of cells in the hypothalamus called the suprachiasmatic nucleus, or the SCN. The SCN is the master clock of the body. When the SCN receives the signal that it is getting dark, it tells the pineal gland to begin its nightly production of melatonin. The pineal gland takes an amino acid called tryptophan, converts it into serotonin, and finally into melatonin, which it then releases into the blood and the cerebrospinal fluid. As melatonin levels rise, the hormone travels throughout the body and brain, binding to receptors that signal a quieting of biological activity. It helps lower your core body temperature, reduces your alertness, and coordinates the many other hormones, like the cortisol and growth hormones we've already discussed, into their proper nighttime channels. Conversely, when the first light of dawn hits your eyes, the SCN immediately tells the pineal gland to cease production. Melatonin levels crash, and the body prepares for the activity of the day. This is a perfect daily loop of chemical timing. It is a system that allows your body to anticipate the environment rather than just reacting to it. Your pineal gland ensures that by the time you actually lay your head on the pillow, your internal chemistry is already set for sleep. Take a moment to let the logic of this celestial connection find its place. Your brain is literally talking to the stars, using the light of the sun to decide how your cells should behave. Even as you lie here now with your eyes closed, your pineal gland is performing its ancient duty, flooding your system with the quiet, cooling signal of the night. To truly appreciate the pineal gland, we must look at how it interacts with the master clock in the hypothalamus. While the pineal gland produces the hormone, the suprachiasmatic nucleus, SCN, is the one that keeps the beat. Interestingly, if you were to place a human in a cave with no light at all, their SCN would still keep a rhythm, though it usually drifts to about 24 and a half hours. This tells us that the rhythm is endogenous. It comes from within us. However, we need the pineal gland and the signal of light to entrain or reset that clock every single day, so we stay in sync with the actual rotation of the Earth. The chemistry of melatonin is also quite remarkable. Because it is derived from serotonin, the feel-good neurotransmitter associated with mood and social stability, there is a deep link between our exposure to light and our mental well-being. This is why many people feel a shift in their mood during the dark, short days of winter. If the day signal is too weak or the night signal is too long, the pineal gland's timing can get skewed, leading to a disruption in the entire endocrine orchestra. Historically, the pineal gland was one of the last endocrine organs to be understood. For centuries, it was noted for being the only structure in the brain that didn't have a twin. Most brain structures have a left and right version, which led to the spiritual speculations of the Renaissance. It wasn't until 1958 that Aaron Lerner, a dermatologist at Yale, isolated melatonin from bovine pineal glands. He was actually looking for a way to treat skin conditions, as melatonin is related to the pigments in frog skin. Instead, he discovered the master key to human sleep. Since then, we have realized that the pineal gland is a remnant of an ancestral eye. In some primitive vertebrates, like the tuatara lizard, the pineal gland is actually connected to a light-sensing organ on the top of the head, a literal third eye. In humans, that eye has moved deep inside, but it still performs the same function, watching the light to time the life of the organism. If your mind is still following along, try visualizing this. Imagine your brain as a great ancient theater. The SCN in the hypothalamus is the stage manager, holding the script and watching the clock. The pineal gland is the lighting technician. When the script says nightfall, the technician slowly turns down the bright white lights of the day and washes the entire stage in a soft, cool, blue-violet glow. This change in lighting doesn't stop the play, but it changes the mood and tells the actors it is time for the quieter, more intimate scenes of the story. You experience the work of your pineal gland every time you struggle with jet lag or the Monday morning blues. When you fly across several time zones, your SCN and pineal gland are still set to the home time. Your body is pumping out melatonin while you are trying to walk through a bright city at noon, or it is withholding melatonin when you are trying to sleep in a dark hotel room. The fog of jet lag is simply the feeling of your endocrine system being out of sync with your environment. It takes about 1 day for every time zone crossed for the pineal gland to re-entrain itself to the new light-dark cycle. In our modern world, we face a unique challenge to the pineal gland: artificial blue light. The light emitted by our smartphones, tablets, and LED bulbs is very similar to the wavelength of midday sunlight. When we look at these screens late at night, we are effectively lying to our SCN. We are telling our brain that it is still high noon. The pineal gland, confused by this signal, delays the release of melatonin. This is why scrolling through a phone in bed can make you feel wired even if you are exhausted. You have manually overridden your body's ancient darkness signal. However, we can also use this knowledge to our advantage. By seeking out bright, natural sunlight first thing in the morning, we tell our pineal gland to stop and our SCN to reset the clock for the day. This ensures that the melatonin timer starts at the right time, making it easier to fall asleep 14 to 16 hours later. The pineal gland teaches us that we are not separate from nature. Our health depends on our ability to align our internal world with the external one. As you lie here now, your pineal gland is at its peak performance. In the darkness of your room, it is steadily secreting melatonin into your system. This melatonin is doing more than just helping you sleep. It is a powerful antioxidant, cleaning up cellular debris and supporting your immune system while you rest. It is the architect of your dreams and the guardian of your recovery. We have now explored the keeper of time. We have seen how the pineal gland uses the language of light and darkness to coordinate the rhythms of your life. We understand the role of the master clock in the hypothalamus and how the hormone melatonin prepares every cell in your body for the quiet work of the night. We have seen how our modern world can disrupt this ancient system and how we can work to restore it. But as we have seen throughout this journey, the endocrine system is incredibly vast. While we have visited the major, dedicated glands, the office buildings of the system, the truth is that the power of hormones is scattered throughout almost every organ in your body. From your heart to your stomach to your very body fat, there are hidden endocrine tissues performing vital tasks we have yet to discuss. Let's hold that thought here, a complete piece of the puzzle. Our next lesson will introduce us to these freelance messengers as we explore other endocrine tissues and hormones. We will see how your heart manages your blood pressure and how your stomach tells your brain it's hungry. But for now, let the pineal gland continue its work. The darkness is here, the melatonin is flowing, and your body is perfectly in sync with the quiet of the night. Feel the slow, steady rhythm of your biological clock and allow yourself to drift further into the quiet. Lesson 9. Other endocrine tissues and hormones. As we near the final stages of our journey, we must broaden our perspective beyond the famous landmarks we have visited thus far. Up until now, we have focused on the dedicated office buildings of the endocrine system, the pituitary, the thyroid, the adrenals, organs whose primary full-time job is the production of hormones. But the beauty of the human body lies in its incredible versatility. In this lesson, we are going to discover that the power of chemical signaling is not confined to these specialized glands alone. We will find that the endocrine function is actually a side hustle for many other vital organs. Your heart, which you know as a pump, your stomach, which you know as a digester, and even your body fat, which many view simply as storage, all moonlight as endocrine tissues. They are the freelance messengers of the body, whispering local needs into the global bloodstream. We are exploring the decentralized network of communication that ensures every inch of your anatomy has a voice in the conversation of your survival. To understand these secondary endocrine tissues, we must first shift our definition of what makes an organ endocrine. In the strictest biological sense, any tissue that secretes a signaling molecule directly into the blood to affect a distant target is performing an endocrine function. This means that even organs with a very clear, non-hormonal primary job can still be part of our chemical network. Let us begin with the heart. You know your heart as the tireless muscular pump that drives your circulation, but it is also a sophisticated pressure sensor. within the walls of the upper chambers and the atria. There are specialized muscle cells that can sense when the heart is being stretched too thin by an overabundance of blood. When blood volume is too high, these cells release a hormone called atrial natriuretic peptide, or ANP. This hormone is a master of fluid balance. Once released, ANP travels through the blood to the kidneys, where it issues a very specific command: release more salt into the urine. Because water always follows salt, the kidneys begin to flush out excess fluid. This reduces the total volume of blood in your system, which in turn lowers your blood pressure and relieves the stress on the heart. It is a beautiful example of an organ taking care of itself through hormonal diplomacy. The heart doesn't just wait for the brain to fix a problem. It sends its own chemical messenger to negotiate with the kidneys. Speaking of the kidneys, they too are far more than just sophisticated filters. While their primary role is to clean the blood and manage waste, they are also the body's primary monitors for oxygen and blood pressure. When the kidneys sense that the oxygen levels in the blood are dipping, perhaps because you have traveled to a high altitude or because your red blood cell count is low, they release a hormone called erythropoietin, often referred to simply as EPO. This messenger travels to your bone marrow, the factory where your blood is made, and tells it to speed up the production of red blood cells. By increasing the number of oxygen carriers, the kidneys ensure that every cell in your body continues to breathe easily. Furthermore, the kidneys work in tandem with the heart through the production of renin. When blood pressure drops too low, the kidneys release renin, which triggers a complex chemical cascade in the blood that ultimately results in the constriction of blood vessels and the release of aldosterone from the adrenal glands. This raises your blood pressure back to a safe level. Between the heart's ANP and the kidney's renin, we see a constant silent tug of war that keeps your circulation perfectly calibrated while you rest. Take a moment to let the logic of this decentralized control find its place. Your heart is talking to your kidneys, and your kidneys are talking to your bone marrow and your adrenals. It is a web of local sensors ensuring that the global environment of your body remains stable. You don't have to think about your blood pressure or your oxygen levels because these organs are freelancing as endocrine glands, managing the details of your survival behind the scenes. If we move our focus to the digestive tract, we find one of the most complex and ancient endocrine environments in the entire body. The stomach and small intestine are lined with specialized cells called enteroendocrine cells. These cells are the border guards of your metabolism, sensing the arrival of food and coordinating the body's response. When your stomach is empty, and has been for some time, it releases a hormone called ghrelin. Ghrelin is often called the hunger hormone. It travels directly to the hypothalamus in the brain, that command center we visited in Lesson 3, and tells it, quite clearly, that it is time to eat, and it increases your appetite and prepares your digestive system for an incoming meal. Once you begin eating, and food enters the small intestine, a different set of hormones takes over. Cells in the duodenum release cholecystokinin, or CCK, and secretin. These hormones act as a stop signal for the stomach, slowing down its emptying so the intestine has time to process the nutrients. They also signal the gallbladder to release bile and the pancreas to release its digestive enzymes. It is a perfectly timed chemical relay race that ensures your digestion is efficient and orderly. Perhaps most surprising of all is the endocrine role of your adipose tissue or body fat. For a long time, we viewed fat as nothing more than an inert storage locker for extra calories. But in 1994, the discovery of a hormone called leptin changed everything. Adipose tissue is actually an active endocrine organ. As your fat cells fill up with energy, they release leptin into the blood. Leptin travels to the brain and performs the exact opposite role of ghrelin. It signals satiety, or fullness. It tells the brain that the body has sufficient energy reserves and that it is okay to stop eating and start spending energy on other things, like reproduction or immune function. In a very real sense, your fat is talking to your brain, giving it a status report on your long-term fuel supplies. The history of these non-glandular hormones is a testament to how much our understanding of the body has evolved. For centuries, we believed the heart was the seat of emotion, and the stomach was merely a vat for acid. It took the rigors of 20th century biochemistry to prove that the heart was an endocrine regulator, and the gut was a chemical laboratory. The discovery of leptin, in particular, revolutionized our approach to nutrition and obesity, showing us that hunger is not just a matter of willpower, but a complex hormonal conversation between our fat stores and our brain. If your mind is still following along, try visualizing this. Imagine your body not as a kingdom ruled by a single palace, but as a vibrant democracy. The heart is the department of transportation. The kidneys are the department of the interior. And the gut is the department of commerce. Each department has its own radio station and sends out its own broadcasts to ensure the whole country stays running smoothly. No one organ is just a silent worker. Every organ is a communicator, contributing its own chemical perspective to the masterpiece of your health. You see the influence of these freelance hormones in the most common experiences of your life. Have you ever felt that food coma after a large Thanksgiving dinner? That is partly the work of your digestive hormones and leptin signaling your brain to slow down and focus on storage. Have you ever noticed how your appetite seems to disappear when you are very focused or very stressed? That is the result of other hormones, like adrenaline, temporarily overriding the hunger signals of ghrelin. Your body is constantly prioritizing its needs, deciding whether to listen to the stomach's request for food or the heart's request for pressure regulation. We also see the work of temporary endocrine organs, the most remarkable of which is the placenta. During pregnancy, a completely new endocrine organ grows within the mother's body. The placenta produces its own estrogens, progesterone, and a unique hormone called human chorionic gonadotropin, HCG. It takes over the hormonal management of the pregnancy, ensuring the mother's body provides everything the developing life needs. It is a transient, disposable endocrine gland, a biological miracle that serves its purpose and then disappears. And we cannot forget the thymus, a gland located in your upper chest, just behind the breastbone. In children, the thymus is large and very active, producing hormones like thymosins that help train the T cells of the immune system. As we age, the thymus gradually shrinks and is replaced by fat, its primary educational work completed in our youth. It reminds us that our endocrine needs change as we move through the different seasons of our lives. As you lie here now, these decentralized messengers are hard at work. Your heart is gently sensing the pressure of your blood as you rest, ensuring it stays at a low, peaceful level. Your kidneys are quietly monitoring your oxygen, making sure your breathing is sufficient for your needs. Your adipose tissue is sending steady reports of all is well to your brain. And your gut is settling into a quiet state of repair. You are being looked after by a dozen different organs, each performing its own silent chemical duty. We have now explored the full breadth of the endocrine network. We have visited the master glands in the brain, the metabolic engines in the neck, the survival specialists of the adrenals, the fuel managers of the pancreas, and the architects of the future in the gonads. Tonight, we have seen how the heart, the kidneys, and the gut join this conversation, creating a truly global and integrated system of communication. We understand that there is no part of you that is truly silent. But now that we have seen all the individual players, the specialized glands, and the freelance tissues, we must take one final step. We must look at how all these different voices come together to create a single harmonious symphony. We need to look at the grand principle of integration. How do all these feedback loops work together to maintain the miracle of balance that we call life? Let's hold that thought here, a complete piece of the puzzle. Our final lesson will bring everything together as we explore integrated endocrine physiology and homeostasis. We will see the big picture, the grand design that allows you to exist as a stable, healthy being in a chaotic world. But for now, let all the messengers rest. The heart is steady, the kidneys are vigilant, and your body is in a state of perfect, decentralized harmony. Feel the quiet efficiency of your trillions of communicating cells, and allow yourself to drift further into the quiet of the night. Lesson 10. Integrated endocrine physiology and homeostasis. We have reached the final stage of our journey together. Over our previous 9 sessions, we have acted as meticulous explorers, taking the great machine of the endocrine system apart piece by piece. We have visited the command centers in the brain, the metabolic engines in the neck, the crisis managers atop the kidneys, and the fuel regulators behind the stomach. We have seen how the heart, the gut, and even our body fat contribute their voices to the internal conversation. But a collection of parts, no matter how magnificent, is not yet a living being. To truly understand yourself, you must see how these parts integrate. Tonight, we look at the grand symphony of the endocrine system. We will explore the master principle of homeostasis, the body's relentless, silent pursuit of balance in a chaotic world. We will see how multiple glands, often separated by the entire length of your torso, work in perfect, simultaneous coordination to respond to a single chill in the air or a single moment of stress. This is the big picture, the grand design that allows you to exist as a stable, healthy individual. To understand integrated physiology, we must first return to the concept that has hummed beneath every lesson we've shared: homeostasis. The word comes from the Greek roots for same and steady, and it describes the state of dynamic equilibrium that your body maintains every second of your life. Imagine a tightrope walker. To the casual observer, they look perfectly still, but if you look closer, you see 1,000 tiny, microscopic adjustments of the ankles, the hips, and the long balancing pole. They are in a state of constant active correction. This is exactly how your endocrine system operates. It is not a static off or on switch. It is a series of overlapping negative feedback loops. In a negative feedback loop, the system is designed to oppose any change from a set point. If a variable such as your blood calcium or your body temperature moves too far in one direction, the endocrine system senses this deviation and releases a hormone that pushes the variable back in the opposite direction. For example, when your blood sugar rises after a meal, your pancreas releases insulin to bring it down. When it drops during the night, it releases glucagon to bring it up. This push and pull ensures that despite the fact that you eat, exercise, and sleep at different times, your internal environment remains as steady as a calm lake. However, the beauty of integration is that these loops are rarely solitary. Most of the time, the body uses multiple glands to manage a single variable, providing a system of redundancy and synergy. Consider your blood pressure. It isn't just managed by the heart's ANP or the kidney's renin. It is also influenced by the adrenal glands' aldosterone and the posterior pituitary's ADH. If your blood pressure drops, your brain, your kidneys, and your adrenal glands all speak at once, each using a different mechanism, holding on to salt, constricting vessels, or retaining water, to ensure you don't faint. This is integrated physiology, a choir of glands singing the same note of stability from different parts of the body. Occasionally, the body utilizes the rare but powerful positive feedback loop. Unlike the negative loop, which seeks to return to the center, a positive loop seeks to drive a process to a definitive, explosive conclusion. We saw this in our discussion of oxytocin during childbirth. The pressure of the baby triggers more hormone, which causes more pressure, which triggers even more hormone, until the event is finished and the cycle can finally break. These are the sprints of biology, designed for moments of profound transition where balance must temporarily be set aside for the sake of a new beginning. Take a moment to let the logic of this grand design find its place. You are not a collection of separate organs working in isolation. You are a single, integrated web of communication. Every push from one gland is met by a pull from another, it creating the steady, reliable foundation upon which your entire life is built. If we look deeper into how these systems interact, we discover the concept of permissiveness and antagonism between hormones. Some hormones cannot do their job unless another hormone has already permitted them to. For instance, reproductive hormones, like estrogen and testosterone, require the presence of thyroid hormones to exert their full effect on development. Without the thyroid setting the correct metabolic pace, the architects of the gonads cannot build the adult body correctly. This is the endocrine system's way of ensuring that the body doesn't try to grow or reproduce if it doesn't have the basic energy resources to sustain it. On the other hand, we have antagonism, where two hormones have exactly opposite effects, like the insulin and glucagon dance we studied in Lesson 6. This antagonism is not a conflict, but a partnership. It allows for much finer control than a single hormone could ever provide. Think of it like the brake and the accelerator on a car. By using both, you can maintain a much more precise speed than you could by just using the gas pedal alone. The body uses these opposing forces to keep its vital signs within a razor-thin margin of safety. The history of our understanding of homeostasis is a relatively young one. It was first proposed as the milieu intérieur, or internal environment, by the French physiologist Claude Bernard in the mid-19th century. And he famously stated that the constancy of the internal environment is the condition for a free and independent life. He realized that because our bodies can regulate their own temperature and chemistry, we are not slaves to our surroundings. We can survive in the desert or the Arctic because our endocrine systems provide us with an internal suit of armor. Later, in the 1920s, the American physiologist Walter Cannon coined the term homeostasis and identified the fight-or-flight response, showing exactly how the adrenal glands were the front line of this internal defense. If your mind is still following along, try visualizing the body as a vast, interconnected ecosystem, like a rainforest. In a forest, the trees, the soil, the water, and the animals are all in a constant state of exchange. If there is a drought, the trees deep root. If there is a flood, the soil absorbs. There is no central computer running the forest, yet it remains in balance through millions of local interactions. Your endocrine system is that ecosystem. Your blood is the river. Your glands are the different species of trees, and your hormones are the pollen and seeds that keep the whole system thriving and resilient. You can see the masterpiece of integration in how your body handles a single day of life. Imagine you are walking outside on a cold winter morning. Your nervous system feels the chill on your skin and immediately sends a signal to the hypothalamus. The hypothalamus, acting as the master integrator, triggers a three-part response. First, it sends a neural signal to your muscles to shiver, generating immediate heat. Second, it tells the pituitary to release TSH, which wakes up your thyroid to increase your long-term metabolic fire. Third, it signals your adrenal glands to release a bit of norepinephrine to constrict the blood vessels in your skin, keeping your warm blood deep in your core. While this is happening, suppose you haven't eaten breakfast yet. Your pancreas is releasing glucagon to tap into your liver's reserves, so you have the energy to stay warm. Your kidneys are managing your blood pressure as you walk, and your pineal gland is noticing the bright morning light and shutting down your melatonin production so you feel alert. This is not 6 different systems working. It is one single, integrated response to a cold morning. Your body is a genius of multitasking, coordinating a dozen different chemical signals to ensure that while the world outside is freezing, your internal city remains at a perfect balmy 98 degrees. We see the failure of this integration in many modern diseases. Diabetes, for example, is not just a problem with the pancreas. It eventually affects the kidneys, the heart, and the nervous system because the fuel line of the city is broken, and every other department suffers as a result. Hyperthyroidism doesn't just make the neck swell. It causes the heart to race and the muscles to waste away. These conditions teach us that you cannot affect one part of the endocrine system without affecting the whole. We are a holistic organism in the truest biological sense. As you lie here now, in the final moments of our study, your integration is at its most peaceful. Your master clock in the brain is coordinating with your pineal gland to keep the melatonin flowing. Your parathyroids are ensuring your resting muscles have enough calcium to remain soft and relaxed. Your heart and kidneys are working together to keep your blood pressure at its lowest, most restorative level. Your body is performing its nightly reset, a process of integrated repair that prepares you for the challenges of tomorrow. You are a masterpiece of self-regulation, a living testimony to the power of balance. We have walked through the 10 lessons of the endocrine system. We have seen the conducting center of the brain, the fuel management of the pancreas, the crisis management of the adrenals, and the architects of the gonads. We have seen the wireless communication of hormones and the target locks of receptors. You now carry within you a foundational knowledge of how your body talks to itself. You don't need to remember every acronym or every molecular pathway. What I want you to carry into your sleep is the profound sense of safety that comes from knowing you are so well cared for. Even when you are not thinking, even when you are unconscious in the sleep, this silent, brilliant system is watching over you. It is balancing your sugar, guarding your minerals, pacing your heart, and timing your rest. You are never truly alone. You are accompanied by the tireless chemical wisdom of your own biology. So take one final deep breath. Let the tension leave your body for the last time tonight. The map is rolled up, the lesson is complete, and the teacher is satisfied. Your body is in perfect, integrated harmony. The music of your hormones is playing a soft, steady lullaby. Good night and rest well.